In the next chapter, we're going to discuss discrete time dynamical systems, or as we will shortly call them, DDS. Discrete means not continuous, so we will produce graphs that are point graphs with measurements taken at some intervals apart and not continuous curves that we generally use so far in calculus for modeling. So here, first of all, a definition of a discrete time dynamical system. It consists of an initial value and the rule, also called an updating function, that transforms the system from the present state to the next one. So we can think of this generally as having some sort of input that corresponds to current state, whether this is current year or current measurement, and the updating function, or this rule that we're referring to, will then produce an output, or next state, next year, or next measurement, or next prediction for some kind of a phenomenon. Now, this updating function is normally what we are after, because if we can find the function that models this process, then we will be able to, given any input, produce a corresponding output. The current state is normally denoted by some variable, let's call it m, sub t for time t, and then of course the next state would be at time t plus 1. The updating function, if we call it f, will therefore take mt as the input in the function notation and produce m sub t plus 1 as its output. Take a look at the first example of such a system. Suppose the initial population of moose is 500, so this is where we're starting from, and that the population doubles every 3 years. How many moose are there in 15 years? So we're starting with 500 moose at time equals 0, which is when our countdown starts, and we can apply our updating function that is our rule for the description of how the population grows or declines. We know that the population doubles every 3 years, so my updating function will be to multiply the current state by 2 in order to produce the state that will be 3 years from now. Now, you can decide how you're going to actually schedule your time, whether every 3 years is 1 unit of time, and therefore the next label will be t equals 1, or you're going to keep 1 year for 1 value of t, and therefore your t will be 3. Either one of those is going to be fine. I'm going to keep yearly count as the years go, and therefore I will have t equals 3. Now, we're asked how many moose are there in 15 years, so we're not quite there yet. We're going to have to go through the updating process again. The population doubles every 3 years, so I take my current value, multiply it by 2 to produce the next one, and then this value will correspond to the year t equals 6. We're not there yet. I will double my current value again. Notice that in the discrete dynamical systems, I will always be working with the current value to produce the next one. I am never looking backwards. I'm looking at the present state and into the future. So the next doubling will produce 4,000 and will correspond to t equals 9. The next doubling will produce 8,000 corresponding to t equals 12. And then the last doubling will produce 16,000 and will land me at t equals 15, which is what I'm after here. If I would like to write down the updating function here, the rule is going to be simple. It doubles every 3 years. So if I, for example, would like to, in fact, specify what the number is going to be, remember again that the input is the current state. I'm going to double it, so I will produce twice mt. Now, this portion here with my labeling, though, corresponds to m sub t plus 3, not m sub t plus 1, because of how I chose to label my years. The other way to think about this, of course, to begin with, is how many doublings are we going to have? If the population doubles every 3 years, there's going to be 5 doublings altogether in the 5 years, and therefore you can shorten this process. Now, what makes the system discrete is the fact that we only take measurements at very specific points in time and not at every single possible point in time. Of course, there's moose here, but we're not recording their numbers except for at specific and very separate timestamps. Now, the long example that we saw last time is also an example of discrete dynamical system with this as an updating function. Remember that we started with x naught as the number of original branches of the lungs, and then in order to compute the next available number of branches, we had to multiply by 1.7 and then by 1.7 again, and so on. So overall, the rule that we described was given by an updating function like this. These types of discrete dynamical systems are in fact very popular, so let's see if we can develop a more general understanding of them. Every time you specify a discrete dynamical system, as the definition mentions, you're going to have to specify an updating function or the rule the system follows and an initial condition. Depending on the initial condition, the final state of your system might be different. So here we're going to first of all analyze this discrete dynamical system. Let's think about what the rule actually states. Recall that x sub t, or anything, whatever you want to call your variable, sub t represents the current state, and if you increase the index, that will represent the next state. So what this updating function is describing is the next state is always double the current state. So similar to our moose example, except for here it happens on a yearly or whatever your unit of time basis is. If we start with initial condition x naught, what are we going to see? For x1, we're going to take the previous state as described by our rule and multiply it by 2. So for x1, we're going to have that it's double the previous state, which is x naught. You can also think of that as plugging in 0 for t in this above formula. So if t is 0, you're going to get exactly this next line. X sub 1 is 2 times x0. For x2, in order to get this next step, you have to double the previous step. So x2 is going to be double of x1. Okay? Now again, you can obtain this formula by plugging in t equals 1 into the updating function. If you plug in t equals 1, on the left you're going to have x sub 2 equals 2 x sub 1, which is exactly what we got here. Now, what we do have, again similar to our long example from last lecture, is that this x1 can be written in terms of x naught. So what I can do is simply take this value for x1 and plug it in here. Therefore, altogether, I'm going to get 2 times 2x naught, and therefore 2 squared x naught. I'm going to keep it as 2 squared so that I'm better able to see the pattern. For the next one, for x3, the next state is double the previous, so 2x2, and x2 is given to me by 2 squared x naught. So I'm going to take this expression for x2 and plug it in. So altogether, I'm going to have double the 2 squared x naught, or if I combine the powers of 2 together, I'm going to get 2 cubed. And I notice a pattern here. For the x sub t, I always get that I have performed t doublings on the initial value x naught. So the general formula for x sub t is 2 to the power of t x sub naught. Notice that this is a much better formula than if I continued iteratively as I did before. If I have to calculate x99, let's say, right, the discrete dynamical systems updating function tells me that I have to double the previous state. So I have to double x of 98. Now, if I don't know x of 98 exactly, that means that I have to work all the way backwards to computing x of 98, and that might of course take a while. So having the general formula or the general solution like this is a very powerful thing here. Let's also sketch two different solutions for two different initial conditions. So this is going to be simply a qualitative sketch. I'm going to try to keep my my scales reasonable, but with exponential things like this, numbers tend to get out of hand fairly quickly. So if I start off with initial condition, let's say of 1, then I will have a point here that corresponds to x naught being 1 at timestamp 0. Every step, things are going to get doubled. So at step 1, I am going to double the previous state at 2, and therefore this is going to correspond to my x1. So let me label my points here, x0, x1. For the timestamp 2, I'm going to double the previous state, so 2, and I'm going to therefore get a 4. 2 times 2 is 4, so at 2 I have 4, and this represents my x sub 2. For the next one, I'm going to double the 4, and that's already going to lead me off where I can't even mark it off. So for x equals 3, I'm going to be up at 8. Actually, let me just put it up here. Let's pretend that this is an 8 here. This is my x3. So notice how this is already quite different from the graphs we're used to drawing. These graphs are going to be point graphs. They're not connected, they're not continuous, because these are in fact the only points that the updating function lets me compute. What's going to happen if I start with a different initial condition? Let's say I start with x naught up at 3. So at time 0, I'm up at 3. At time 1, I'm already up at 6. So up here, this is my x1. And at time t equals 2, I'm going to be double that. So I will be then up at 12, which is already off of my screen. Exponential functions grow very quickly. We can summarize all of our findings with this particular statement that the discrete dynamical system given by this general rule, where in example above b is equal to 2, if I have an initial condition x naught, then the overall solution, which means that an explicit formula for x sub t given only the value of x naught is my factor b up front here to the power of t, corresponding to the number of steps I had to take, times x naught. So times my very, very first initial state. This is why these functions are called exponential. This factor, when you take more than one step, will be compounded on top of each other, on top of itself, t times, therefore producing an exponential looking curve. These discrete dynamical systems describe things like population growth or bacteria doubling or anything like this quite well. If this number is less than 1, then we get the decay type models. So radioactive decay, the breakdown of drugs in our system and whatnot. The other types of discrete dynamical systems are what's called additive. So in this case, instead of multiplying by a constant factor, we will be adding. These types of things are nature processes that are described with constant growth. For example, a tree that grows a constant of 0.8 meters every single year, independent of its current size or height. So what's going to happen here? How is the solution and the overall behavior of this model going to be different from the exponential one? If we start with W naught, so our initial condition, what the rule says is for the next one, I simply add 0.8 to the previous state. So to compute W1, I will take W naught plus 0.8. Again, you can think of that as plugging in t equals 0 into the formula above, and then you will get this exact same expression. For W2, again, to compute the next state, the updating function tells me to compute the next state, I have to take the previous state and add 0.8 to it. So I take the previous state, which is W1, and I add 0.8 to it. Now, I'm going to do the same thing I've done before. W1 is actually equal to that, so I can replace W1 with this expression in the line for W2. So altogether, I'm going to get W0 plus 0.8 which is the expression for W1, plus the 0.8 that I inherit from the second step. I can open up the brackets and put together my 2 0.8s, but I'm actually going to keep them uncalculated like this so that I see the pattern. For the next step, I'm going to take the previous step and add 0.8 to it. And again, what I can do here is replace W2 in this expression with the expression that I've just derived earlier. So I'm going to take this whole thing and replace W2 with it. What am I going to get? I'm going to get W0 plus 2 0.8s plus 0.8 more. 2 apples plus 1 more apple is 3 apples. So I'm going to get 3 times 0.8. For WT, again, I can compute it using my updating function rule, which is exactly just this, or I can already notice the pattern here, that what happens at every step is that I add another 0.8 to the summation, and therefore I can generalize this pattern. By the time I get to the tth step, I would have started at my initial condition, and I would have added 0.8 t times. Okay? Now, again, having a separate formula in terms of just the initial condition and the number of steps that are needed for this is much more essential, because otherwise, in order to compute, for example, W5, I would have had to find W4, which means I would have had to find W3, W2, W1, and so on. In order to avoid going through this chain of computations, having an explicit formula for any given t is a powerful thing. Let's try to sketch what the solutions to this model will look like. To this particular one, let's say with 0.8. Okay, so again, timestamps 1, 2, let's say 3, and 4. What if I start at the initial condition? Let's say I start at 1. Why not? So this is my W0. What my pattern says is I have to add 0.8 each time. So at time 1, I'm going to have 1.8 added to my overall number. So I'm going to be at 1.8 here, and this is going to be my W1. For the next step, I'm going to add 0.8 more. So I'm going to then be at 0.8 higher at this step for W2. And if I can do my math correctly, 1.8 plus 0.8 is going to be 2.6 up here. Continuing on in this manner, I will keep adding 0.8 further and further away. Okay, so what we notice here is because I constantly add 0.8, I am actually creating these points that lie in, if it were continuous, a line. What would happen if I started with a different initial condition? So let's say I start, like I did last time, with 3 as my W0. The first thing I would do is add 0.8 to compute the value at time equals 1. So this will be at 3.8, and this will correspond to my W1. The next one will be at 4.6 and will correspond at W2, and so on. W3, and so on. What I notice here is these guys also lie in the exact same line. This is creating a slope. And in fact, it's fairly clear from this formula that what I get is a line, because t is to power 1 here, and this is its slope, 0.8, whereas this represents the y-intercept, where it all starts. Now again, because it's discrete, I'm not actually going to get a continuous line going through these points, but that doesn't mean that I can't envision them lying in a line, because that's exactly what's happening here. So overall, if I have a discrete dynamical system that says that the next state is computed by the adding of the constant a to the previous state, then my solution, and that means the explicit formula for WT, will be the initial state plus t times this value of the constant additive factor. This is why these systems are called additive, because we add things here and we end up adding them everywhere. And the solutions, independent of the initial conditions, will always be these parallel looking things with always the constant distance fixed in between them. Our next example of a discrete dynamical system is our most complex one yet, so we're going to work through an application to set it up. Suppose a patient is on methadone, which is a medication used to relieve severe pain, for example, after a surgery. It is known that every day a patient's body absorbs half of the drug. To maintain appropriate level of the drug in the system of the patient, new dose containing 1 unit of methadone is administered. It says at the end of the day. Let's fix it to be the beginning for easier modeling here. So let's think about what process happens throughout the day. I will start with the morning amount of the drug in the patient's system. Now, by the end of the day, so let's say that every day means 24 hours. So the next morning, we're going to have half of the current amount. And at the beginning of the day, 1 more unit of methadone is going to be administered. So there is the next morning amount, and then there's a different amount after the additional dose. Now, this is an important process, of course, to model because we want to make sure that the amount of drug stays above a certain threshold so that the patient is comfortable. If we're going to let m of t denote the amount of methadone present at some time t, let's say that t is going to be a morning measurement. By the next morning, there's going to be only half of that amount in the system, and after the additional dose of 1 unit, we're going to have half of the previous amount of the drug plus the 1 unit. So overall, our updating function for the next after additional dose morning amount of methadone is half of the previous morning's amount plus the 1 additional dose we have administered. Now, this process is going to be iterative, which means that we're going to repeat this not for just one 24-hour cycle, but again and again and again. So what we would like to do is trace the amount of drug in the system at any point in time. If we start with the loading dose of 5, how does that affect the amount of drug in the system? Can I say what it will be 3 days from now? Now, this might seem like a large number given that every day we only supplement with 1 additional unit, but a so-called loading dose is always high. This is the dose that's given immediately after the surgery to make sure that the patient is comfortable right as they wake up. So if we start with 5, recall that our overall updating function is 0.5 mt plus 1. So we take the current amount, half it, and then add a 1. So we can apply this rule to m naught and any other number of measurements we care to predict. So for the first one, I'm going to have half of the previous plus 1, which ends up being 3.5. I'm going to write out the next few, and I encourage you to actually do the calculations to get a hang of this iterative way to compute these numbers. Now, what we can do is try to see what the pattern is, but in these linear discrete dynamical systems, the pattern is really quite complex, so we might not be able to see it from the numbers. Let's try to graph it and see if we can spot something from the graph. On this graph, we're going to sketch time versus the amount of drug in the system. So at time t, we start off at 5. At 1, we're at 3.5. At 2, we're up at 3.75, 3.375, 3.18, and we get closer and closer to 2. The question, of course, really is, where is this all going? Does it look like it approaches 2, or will we drop off and then cross over under 2? If 2 is our desired threshold of where we think the patient is going to be comfortable at, this is probably a good pattern to have. Now, if you actually are incredibly good at spotting patterns, what you might notice in the graph is that the distance between any 2 consecutive steps, the vertical distance, actually decreases by half every single time. But this is not something that we generally will be able to spot right on. So we will need to develop some other methods of figuring out what is the teeth value of the amount of drug in the system on the teeth day without relying on being clairvoyant when it comes to patterns. The other thing that I suggest you do here is start with a different initial condition, for example, 1, and see how that will play out in computations and therefore on the graph.